In this section, we're going to talk about variations. The idea of variation is to investigate or find out relationship among variables in a geometrical or physical engineering application, or it could be other applications, as long as we're interested in relationship among several variables. So for example, let's say something being math. I'm going to make an example from geometry. The area of a triangle, 1/2 base times height. So this formula shows a relationship between area and the size of a triangle. Now, we can investigate how, in fact, the area varies in relationship to the base and the height of the triangle. Okay, so another example, for instance, if we have force mass times acceleration, we can investigate how force changes in relation to acceleration. Therefore, we're going to investigate these variations, each in its own way. And we're going to first classify the types of variations, and then we look at some application problems. So there are, broadly speaking, there are three kinds of variations. We have what we call direct variation, and we have a reciprocal or inverse variation. And then we could have possibly what we call joint variation, where you have a joint combination of two or more variables, such as M and A in my F equal MA example. And so we're going to call joint also combined variation. So those are the types we're going to look at. Now, first of all, what is direct variation? In case of direct variation, we can actually write, if I call the variable generally y, we can say variable y varies directly as x if the relationship between them is in the following form. If I can write y equals a constant multiple times x. Okay, so there you go. Now the reason it's called direct because as x, for example, increases, as x goes, as x, depending on k, of course. Let's say k is positive. So in that case, as x increases, that affects y directly. Y increases also. If x decreases, then y decreases as well. Again, depending on k, but that's the idea of direct variation. Okay, now the variable y in this case could vary as, say, some power of x, right? So we could have the nth power of x. So another special case would be kx to the n. So in this case, y varies directly with some power of x. Okay, now what does the role k plays here? K is called the constant of variation, okay, or constant of proportionality. That's what we're going to call k. K is constant of variation or proportionality. And that's what that is. All right, and k is different from 0, by the way. It's a constant because if it's 0, then we have nothing. Everything is 0. So it's what makes the equal sign actually work. So for example, to show you the role k plays, I could say that, for instance, that the price of your car is proportional to, let's say, the age of your car. The age of your car. Okay, so in this example, price proportional to age. So I have two variables, and this is how we can say it. And because it's age that determines the price, not the other way around. Price doesn't determine the age of a car, but age does determine the price of a car. So I can say price P, and then I'm using this symbol as a proportionality symbol, is proportional to A if I call A the age of the car and P the price. So I can write it in this relationship like this. When two things are proportional, that means if you take the ratio of them, in this case say P divided by A, that ratio actually approaches 1. This ratio approaches 1. It becomes 1. Or if you do A divided by P, it doesn't matter. So that's what proportionality means. So I'm using this tilde as a proportionality symbol. Now, we want to be able to practically, we want to determine the price of your car based on the age, right? The symbol doesn't help me. So now I can actually come up with an equation that replaces this proportionality symbol with equal symbol. But in order to do that, I need a constant that multiplies by A, which will produce the price, whatever that constant might be. Okay, and of course the key is how do we determine that constant, right? Which remains to be seen. So there you go. Now I have an equation. I don't have a proportionality. I have an equation in P and A. So give me the age, I determine the price of your car. So that's the role that K plays in this situation. K actually establishes this relationship. And notice, by the way, the units. P is the price, age in years, for instance. So K actually has units. This K, in my case, if I do divide both sides by A, the units of K would be dollars per year, wouldn't it? So keep that in mind, that constant of proportionality actually carries the units with itself. Otherwise, these equations would be meaningless in terms of the units. Without the K, I would say dollars equal years, which physically doesn't sound right. All right, so that's the direct variation. Now that we discussed the role of K, we can talk about the other ones quickly. When we talk about inverse variation now, Y varies inversely with X. That means X is now the denominator of a fraction. So there's that reciprocal relationship between Y and X, and K plays the same role here. K is the constant of proportionality. And of course, Y could vary with some power of X, right? So for example, could be the cube, could be squared, whatever the power of X might be. All right, and that is what inverse is. Then we have joint or combined variation. For joint variation, then Y varies with, for joint I need to have 2 or more variables. So I'm just going to go with 2K and call it XYZ, so that would be Z. And remember, K is always in every one of these. K is what causes the equal sign to work and the units to kind of relate to one another. So that would be the joint variation. So for example, I could have Y varying jointly, and there's my K. Notice K is always being multiplied here, right to the right of equal sign you have K. So K doesn't show in the denominator or a power or anything. It's just in front of the equal sign. It's the variable that could show in front. If it shows in front, then it is direct variation. See, like in this case, I have direct variation, and let me use a different color here to outline this. So that's my direct variation. K is directly in front of equal sign, and X right in front of equal sign to the right of K. And here, notice for reciprocal or inverse, K appears in the denominator. And for joint, it's just whatever the two other variables are on the right side of the equal sign. Now, for instance, Y could vary jointly with the nth power of X and the nth power of Z. So those are possibilities. Now, when we talk about combined variation. Combined variation could have what? It could have one or more of the variation types, okay, in it. Remember, there are three types we talked about. We talked about joint, inverse, and direct. So an example of a combined variation, for example, I can say W varies, let's say, jointly with square of x, and cube of m, and inversely with the fourth power of z. You see that? That would be an example of a combined variation. Doesn't have to be powers, by the way. I can say q varies directly with, let's say, square root of x, and inversely with the third root of w. See that? So it just depends on the relationship between the variables. So let's talk about and look at some examples, and we'll see how this works out with some basic applications. All right, so here I made up an example. Let's say we have two variables. I've written y varies directly, so notice how I have very specifically indicated the type of variation. Y varies directly as x. Y is 20 when x is 4. Let's say that's known. And we want to find y when x is -6. All right, so initially, that first piece of information that I'm given, well, at the very first, the direct variation allows me to write the kind of equation that I need, y equal kx. That just follows from the type of variation. Now, once I have that, then I put the specifics of what's given. I'm told y is 20 when x is 4, so I have k times 4. This information, notice, allows me to solve for k and identify what k is. So k would be 5. This is the constant of proportionality. Now, once I have that constant, I can update the equation. This is now the final equation, which shows a functional relationship between x and y. Now give me an x, I can give you the y. So we want to find y now when x is -6, so y would be 5 times -6, and the answer is -30. So see how that works? It's typically what happens with these variation exercises or problems. You're given the type of variation or association, and then you're given one piece of information that allows you to find the constant of proportionality, and then you have the final updated formula. Okay, I'm going to make up another one. This time, let's say I'm going to change my variable so we are not hooked on x and y's. Let's say this time I say m, whatever m is. Let's say m varies jointly this time. Okay, I want a joint variation as, let's see, m as, let's go with n and p. So I have m and p. All right. Now let's say m is 10. Okay, let's make that 10 when n is 2. And let's make p 14, something like that. And p is 14. Let's say we want to find m now when n is 21 and p, whatever, 8. So let's see how this is going to work. Again, the type of variation brings out the formula. So m, there is your k. See, as soon as you write that, regardless of the type, you have the variable equal and then k times. Now the type of variation is joint. So I'm going to join n and p together. There you go. Jointly with n and p. Now notice, by the way, joint variation, let me go back up here. Joint variation implies, this implies direct. See, notice how it's directly changing with x, directly changing with z. in the general form. So the fact that I've said joint, I have to put n times p, not n whatever p. Has to be direct with each of those. Now let's see, m is 10. So when m is 10, here's k, n is 2, p 14. So from this I get k is, divide both sides by 2, so I get 5/14. And that's the value of k. Now I can update 5/14 times np. So this becomes the general formula that connects the three variables. Now I can use it to answer the question. We want to find m. That's going to be 5/14 when n is 21 and p is 8. Okay, so let's see. Let me divide the 2's. That would be 7. This would be 4. And yeah, 7 times 3 is 21. So that's going to be 60. The whole thing is 60. So I would expect m to be 60 with that given information. Okay, so we looked at the direct, we looked at the joint. Let me make up an example of, I don't know, inverse. How's that? Let's say y varies, this time inversely. Okay, so y varies inversely as x again. And let's say, suppose, I don't know, whatever numbers we can make up. That's 10. And sorry about that. So y is 10 when x is 3. And we want to find y when x is, let's go 20. All right, let's see what happens. Varies inversely. So here's c equal and then k divided by variable. Now y is 10 when x is 3. Multiply both sides by 3, so I get k to be 30. My constant of variation is 30. That's going to be y equals 30 divided by x. And now when x is, so this is again the general formula. And now specifically when x is 20, you go 30 divided by 20 or 3/2. That's what y is. And we have that one. See how that works? Now, so that's the general idea. Let's actually try to work out, I don't know, let's try to work out an example here. Okay. In this example, I'm going to find one from the book actually real quick. All right. So here I have an example. We're going to try to work this one. So in this example, Hooke's law, this is from physics. Hooke's law for an elastic spring states that the distance a spring stretches varies directly as the force applied. If a force of 15 pounds stretches a certain spring 8 inches, how much will a force of 30 pounds stretch the spring? Of course, we can see that's twice the force, right? So you would expect the answer to be twice as it used to be, right? Now the 8 inches is beyond the spring's natural length. Remember, this is the spring's natural length. That means before any force is applied to it. Okay, so we're told that it varies directly. That's all we need. So I'm just going to write this as, let's say distance, we're going to call it d, is equal to k, direct variation, directly varies with force. Now we're given that if a force of 15 pounds stretches the spring to the tune of 8 inches, that would help me solve for k, right? Divide both sides by 15. K is 8/15. If you want the units on this, would be, because I divided, let's see, it will be inches per pound. You see that? I did mention k has a unit. So in applications, you can see the units on k. That's the spring constant, they call it, for that particular spring of that particular material. And depending on how many, I guess, loops there are in that spring. Now, to answer the question, how much will a force of 30 pounds stretch the spring? Now, I can update the formula, right? Plug in the K and then times F. And with this, I'm going to get D is equal to 8/15 times force. The applied force is now 30. And we can simplify it, 16 inches. So you see how simple that was. And that would be an illustration of the direct variation. Let's take a look at another example. All right, here's another example. In this one, the speed of a pulley varies inversely as its diameter. One kind of pulley with diameter 3 inches turns at 150 revolutions per minute. That's the RPM, the familiar RPM. Find the speed of the similar pulley with diameter 5 inches. Okay, so I'm just going to let S represent the speed of the pulley. And because we're told that it varies inversely, so here's your constant of variation. And I'm going to put D in the denominator for diameter. Now we are told that one kind of pulley with a diameter of 3, this one turns at the speed of 150 RPMs, right? And that will give you K. So in this case, multiply both sides by 3, you get 450. The units on K are inches RPM. Okay, which I don't know, whatever. It may be meaningless, but once we put it in the equation, then it causes this equation to work. Because the units must be consistent, also work as well as the equation does. And here's the updated formula for this. And now I can plug in, find the speed of the similar pulley with 5 diameter. So the speed is going to be 450 divided by the 5, and that's going to be 90 RPMs. You see that, how simple it is? So identify the type of variation and use the given information, provided information, to determine constant of variation. All right, let's take a look at this last example. So this one, something you're familiar with, the body mass index. The federal government has developed the body mass index, or commonly called the BMI, to determine ideal weights. A person's BMI is directly proportional. Okay, so that's key piece of information. So I'm going to call I for the index. It is directly proportional. So here's K to his or her weight. The W, let W be weight, right, in pounds, inversely proportional to the square of his or her height in inches. So that would be H in inches. Now we're told it's inversely proportional to the square, right? So I'm going to go H squared there. That gives you the general equation before we determine K, constant of proportionality. Now, a 6 foot tall person weighing 170 pounds has an index of 24. So I'm going to go 24 is equal to K times 177 pounds. Now, we're told that height is in inches, right? The height of a person is in inches. If you're given 6 foot, a person who's 6 foot, you multiply times 12, that would be inches to a foot. So that person is 72 inches tall, right? So I'm just going to put 72 and then you square it. This will solve for the constant of proportionality. Let me put the step in there. You multiply both sides by 72 squared and divide both sides by 177. So it's 24 times 72 squared divided by 177. And this number should be, let me And there we have it. I went ahead and multiplied the top, divided by 177. So this is the constant of proportionality. Now I can update my BMI formula. That's going to be 124,416 W divided by 177, right? And then H squared. You could use a calculator to approximate it, but I don't like to, because if I round too early, because this number is going to give me a decimal, it's not going to be a whole number. So if I round now, then my answer in the end would have too much rounding error. So I'd rather to keep things exact until the very last step. So there we have it. So we have this formula now. This is the updated formula for this body mass index problem. Now let's see, we are told a person, we want to find the BMI of a person now who is 66 inches tall, 130 pounds, 66, 130 pounds. So the answer would be 124,416, 130 pounds, and the height was 66 inches. Yes, divided by 177 times 66 squared. And let me do this computation. Okay, and what I got was 20.98 for this one. And we are told to round the number, right, to the nearest whole number. So to the nearest whole number, this number is going to be 21. Therefore, the index, the BMI index, is going to be 21. So it looks like it's in the recommended range of 19 to 25. Good for that person. All right. So that's all there is in this section we're going to talk about. We took on the idea of variations, direct, inverse, and of course combined. The last one we did, the one we just did, this is an example of combined variation. You see that? Because we have both direct and inverse. So that would be an example of a combined variation. All right. So we're good. Thank you for watching, and have a nice time.